Hello, you're welcome again, and today we'll be looking at the properties from the operation table, and this is the aspect of abstract algebra where we get to dive in gently. So the first property from the operation table is a closure property. Remember, we have property A and property B in group G. So this is what the closure property states, that an element A in G and an element B in G, when they are performed together by an operation, either addition or multiplication, their result is actually going to be in G, and G must be a non-empty set. That's trying to tell you that if A in G here is 0 and B is 1, 0 plus 1 equals to 1, and you see 1 is still inside G. If we have 2, 0 plus 2 is 2, 1 plus 2 is 2, 1 plus 3 is 4. Now, on a case like this will be on modulo 5. Remember, we had the first, go back to the previous video, and we worked on this with modulo 5. So if 1 plus 4 is 5, we have 5 divided by 5 gives us 0, remainder 1, and 1 is inside this set. So that is how the closure property is satisfied. The next is the associativity property. So the associativity property states that in parentheses, if A performed by B, closed bracket, is performed by C, it's going to be the same thing as when A is outside the bracket, performed on the operation B and C. Whenever you perform these operations together, the results will definitely be in G. The next property from the operation table is the identity property. Feel free to go to play the video faster if you are already conversant with this part. So the next property is the identity property, where we say there exists a unique element E in G such that A performed on E equals E performed on A gives us A, and A will definitely be in G. Then the next is the inverse. The inverse here is saying that there exists a unique element A in G such that when A is performed on the binary operation by its inverse, the same operation still gives us E, and A inverse will be inside of G, where A raised to power minus 1 is inverse of A. And then the last property is the commutative property, where A asterisk B will be equals to B asterisk A, and A and B equals to G. Just for example, if we have A equals to 0 plus 1 equals to 1 plus 0, our answer is going to be 1 equals to 1. That is what this is trying to tell us, and we have A and B in G. So let's note now the aspect of abstract algebra where we dive in. We get to note that for a set to be called a groupoid, it's only actually going to have the closed property. For a set to be called a semigroup, it's going to be both closed and associative. For it to be called a monoid, it's going to be closed, associative, and identity. Those would be the three properties for a monoid. That's for the set G. If it satisfies only these three properties, it's going to be called a monoid. For the set G to be called a group, then it's going to satisfy the closed, associative, identity, and inverse. And for it to be called an abelian group, is going to satisfy the closed property, associative property, identity, inverse, and commutativity. I'm going to see you in the next video. Feel free to write in the comment section below if you have any issues with it or where you want us to clarify you more. Don't forget to like, share, and subscribe. Thank you.